Hey, so in this lecture, we will see how do we maintain consistency or how do we handle consistency in a key value store designing. So till now I have spoken about two topics or two frameworks, which is the data partition and data replication. So what is that in a brief is like the keys are distributed evenly among the servers to minimize the data movement whenever the server is down. And not only that, to a particular server the key is confined to, the servers replicate those keys into multiple other servers to achieve high reliability and accessibility or availability. So now let's look into the nitty-gritty of how these write operations or put operation and how the read operation or read operation works. So for that, we'll get back to our topic, consistent hashing, where we had a hash ring and we had those servers mapped onto the hash ring. So let's say I'll work with currently n equals to 4 servers. So eventually, firstly, the servers have some capacity or data size which they can hold, or we can consider it to be some hash numbers which they can hold. So suppose let's say S1 can hold up to 1 to 50, S2 can hold up to 100, 51 to 100, S3 can hold 101 to 150, and let's say they have the similar capacity or similar size, so and 151 to 200. So now we want to do a put operation, put key value. So let's say this is an apple, whenever, and this is the key. So let's say this is a ID 143. So whenever we perform a hash of key, so let's say 143 and it maps to 42. So we see this number, we check which server holds this range or which range this number falls into, and we can find out this is S1. So this S1 for this data is termed as its coordinator. Just remember this term. So what is a coordinator? So if you define in English, you can say, like, if we calculate the hash value of a key and the value falls into a range of a server, that server is considered as the coordinator for that key. So you can remember in this way. So like if I have a key, I calculate the hash value of it and I'll check the range in which that number falls into or belongs to, which server holds that value, can accommodate that value, and that server belongs to, or that server is called the coordinator for that key. Now we had heard about the thing like data replication. Now the key has been put into server 1. But earlier we had learned about data replication also. So this key has to be replicated into other servers. So now let's say suppose I consider number of replicas which I want for this data or for this key is 3. So apart from server 1, I need, so let's say this is R, I denote by R minus 1 servers to put this key. Let's say I name it key 1, put key 1, put this key 1. So how will server 1 know which server to replicate this data, or how will coordinator know which servers to replicate this data? So here every server has its own preference list. In consistent hashing algorithm, every server is given its own preference list. So this is a preference list. So what is a preference list? So if you check for, say, let's say suppose this is my server. So my server 1 has a preference list like this, where S1 is in the first preference since it is itself, and this is the coordinator also for key 1. S2 is the second preference list, and S3 is in the third preference list. So now when I have a put request, I'll check the preference list of coordinator, or for rather I say server 1. I see I need to do R-1, which is in this case 2 more replicas. I check the preference list and I put key 1 here also and key 1 here also. So data is replicated here, data is replicated here. And mind you, as I have also mentioned in the data replication part also, so this replication of from S1 to let's say S2 and let's say S3 of put key 1 comma apple is happening asynchronously. So now you have an idea how this put request for a particular key value pair of a client happens and how is this data being replicated. So we have introduced two terms. Just to recap, this is coordinator. So coordinator is nothing but the first hash value which we get for this particular key, and this value which falls in the range of that server holds, that server is the coordinator for that key. And we check then the preference list of that server. We check how many replicas we want of that key, and we accordingly put that keys into the servers as per the preference list. Now this is how a put request is handled. What if I want a get request? Or what if I now want to read the data? I hope this is clear to you how this works. So now I'll look for get request. So earlier I'll just, this one is S1, this one is S2, this one is S3. This was the coordinator. And this is the number of replicas which we had earlier, and the data is being replicated into 3 servers since we had 3 replicas. Okay. Now we are looking into a get request of key 1 from client. So whenever we have a get request, it first is directed to a load balancer. So this load balancer handles this traffic and eventually distributes this request to a particular server. So it is handled in broadly 2 ways. One is the generic load server, you can say, load balancer, sorry. And another is the partition load balancer. So generic load balancer, whenever a request comes, so ideally, what is this? So if I see this is K1, so it should put into its coordinator, the server 1. But what generic load balancer does, it can send request to any server. So let's say the request is being sent, get request is sent to server 0. So now server 0 looks into its preference list. So mind you, I just want to mention every server has its own preference list. And each server is aware of every other server's preference list. So when S0 receives this key 1, it checks that S1 is the coordinator for this key. So what it does, it sends this request to S1 to handle. So this method of sending the request for S1 to handle after identifying that S1 is the coordinator for this particular key, this is termed as hopping of request or hopping. So what is hopping? Sending request to the actual coordinator. Just remove this. Yeah. Sending request to the actual coordinator. So now once the request is being sent to S1, it identifies the key and it returns the value to the client. Whereas partition load balancer is a little bit intelligent, it has a stateful set and it works on data partitioning method and it directly sends the request to your key 1, server 1, and server 1 returns the value. Okay. What if the server 1 is down? So let's say suppose the request has come to S0 and S0 identifies it server 1 and server 1 sends the request to server 1, but the server 1 is down. In that case, the preference list is being checked by the load balancer. It checks the preference list and it sees that S2 has the data. Here comes the benefit of data replication. S2 has the data, so it sends the request to S2. S2 is up. S2 now returns back the data to the client. So in this way, this preference list comes to help in this case. So now the question is, so I hope you get an idea how now the GET request or the read request works. When a client places a read request, it eventually goes to a load balancer. Just a recap of what happens. It goes to a load balancer. Load balancer is basically of two types, a generic load balancer, partition load balancer. Generic load balancer, what it does, it can send the request to any server blindly. Then the server checks the key, maps, it has the preference list and it has the knowledge of every other server's preference list. It maps the key to its particular coordinator and then the coordinator handles the request. If it's up, it returns the request or returns the data for the corresponding key to the client. And if it's down, it checks the preference list and sends the request to the next preferred server, and then that server returns back the request to the client. So this generic server method has some drawbacks also. So basically it has high latency and it's easy to implement, although. Easy to implement, yes. So now, what if we want all the requests to be synchronized across all the replicas? Mind you, the data is being sent asynchronously, but we want the data to be consistent across all the replicas whenever we put a write request or a read request. In that case, we have quorum consensus. What is that? Don't get frightened by the term. It's nothing. It's a simple thing. So I'll go into it. Let me clean the board. Yes. So I want consistency across replicas for write or put and for read or get. So here we introduce something called quorum consensus. What is that? I'll denote three terms first. So here N is the number of replicas, W is quorum size W, and R is quorum size read. Okay. So this is nothing but a simple thing which we'll understand very easily. So let's get back to our basic architecture. Hashing, we have our server 1, key 1 is put here. I have a put request. Suppose first we are handling a put request, key 1 value. Data is this one, and this one. I had this reference list of S1, S2, S3. This is the coordinator. So when the put request comes, it replicates the data to S3 and S2 happening asynchronously, and they also send their acknowledgement that data has been written here. Each server sends its acknowledgement to S1 that data has been written or put successfully into the servers. So what does quorum size W represent? So W says that if it is a certain value, let's say A, so server 1 will send a successful response to the client. So to the client if it gets at least A acknowledgements from other servers. So what it says actually is, so if I put W some numbers, say let's say W is 1. So in spite of the fact whether S3 or S2 sends an acknowledgement, if S1 receives any one of the acknowledgement, from one of the servers, either S2 or S3, it will send a successful response that put has been performed successfully. And similarly and analogously, you can put for R request also. So where R stands for read, and this is performed during get operation. So what it does in get operation, that so the server S0 waits for response from R replicas or servers to consider or send a success response to client for get. So it waits for at least R replicas to send acknowledgement so that it can send a successful response to the client for get operation. So this is performed to maintain the consistency or maintains the synchronization across replicas for data. So there is a trade-off between W, R, and N for 1. Latency, 2. Consistency. It's a trade-off. Why I'm saying a trade-off? Can you think of it? Why it is a trade-off? So let's say W is 1 or R is 1. So this is a low latency performance. However, if W or R is greater than 1, it has to wait for more than 1 replicas to send successful response. Although this offers better consistency, like we have more number of replicas to ensure that the data has been written or we get a consistent result performing put operation or get operation respectively. But this is a low latency and this is a good performing architecture. So this is the trade-off between this. W, R, and N. So if R plus W is greater than N, then we say there is strong consistency. So what is strong consistency? Strong consistency, or why do we say it is a strong consistency? Because there could be at least one overlapping node that has the latest data to ensure consistency. What I said is, so suppose W is 2, N is 3, and R is also 2. N is 3 is N replicas, so S1, S2, S3. So I have two nodes to ensure me or to get a successful response for a write operation, and similarly I have two nodes to get a successful response for a read operation. So there is at least one overlapping node which has the latest data and which ensures it has the latest data for consistency. So this is a condition where we have a strong consistency. For the architecture which we are studying, this is key value store, and these are implemented by the databases like Cassandra or Dynamo. They don't although follow strong consistency. They rather prefer what we can say is availability over consistency. And for this, what they favor is eventual consistency. So now we will deep dive into what is this eventual consistency, how it is being achieved, and how does it ensure the data is consistent after multiple read and write operations. So we'll look into this in the next section.